Welcome everyone. In this lecture, we will learn about the concept of electromagnetic waves in lossy dielectric medium. In previous video, we have discussed about electromagnetic waves in perfect dielectrics. Only displacement current is considered in perfect dielectrics and they are lossless. But practical dielectrics can be lossy. We may have a conduction current in addition to the displacement current. Though the electric conductivity of a dielectric material is very low, still we need to investigate the features and characteristics of dielectric materials with considering their conductivity. We will start this video recalling the general Maxwell's equation in the point form in frequency domain. Then the equations will be tailored for a source-free, homogeneous, lossy dielectric. The obtained equations are to be used for driving wave equation. Such wave equation is a non-homogeneous differential equation. We can transform it into a homogeneous differential equation by incorporating the conductivity and permittivity together to form a complex term called the effective permittivity or the complex permittivity. Then we will introduce with loss triangle and loss tangent. The solution to the wave equation in lossy medium will be interpreted mathematically and graphically. Finally, we will solve some numerical problems for lossy dielectrics. The point form of Maxwell's equation in frequency domain are listed here. The equations are rewritten for a linear, homogeneous, isotropic, source-free, lossy dielectric medium. We replace B and D with mu H and epsilon E respectively, and we consider the conduction current density in addition to the displacement current density. As we consider the system is source free, so there will be no current source, so the impressed current density will be 0 and no charge source. Therefore, the convection current rho Vs U will be 0. So for lossy dielectric, you can see the modified expression for the Maxwell's equation. And then we take the second equation where j omega epsilon taken as a common factor, and we got j omega epsilon times 1 plus sigma over j omega epsilon times Es, where epsilon with 1 plus sigma over j omega epsilon is called effective permittivity or complex permittivity, and we replace this with a new parameter, that is epsilon E. And some textbook they write it epsilon C for complex permittivity, but in this course we will use epsilon E for effective permittivity, and effective permittivity is equal to permittivity times 1 minus J sigma over omega epsilon. We move J on the top, and that's why we change the sign plus to minus, because minus J square is equal to minus 1. So if you take J square on the top, that will be minus J square, and the denominator is j. So you cancel out j square over j, it will be negative j. The complex permittivity has a real part and an imaginary part. We rewrite epsilon E is equal to epsilon times 1 minus j tan theta L, where theta L is called the loss angle and tan theta L is the tangent of the loss angle and it is called the loss tangent. Look at the diagram here. The ohmic current density term, that means the conduction current density term, is in phase with the E field, and the displacement current density j omega epsilon E term, that is is perpendicular to the E field. With considering the conduction current density and the displacement current density, we can produce a triangle, a right angle triangle, which is called loss triangle, where one side of this triangle is the conduction current density sigma E and the other side, the perpendicular side, is j omega epsilon E is the displacement current density. The angle tangent tan theta L is equal to sigma E, the conduction current density, over the displacement current density. So the loss triangle can also be defined as the ratio to the magnitude of the frequency domain conduction current density and the magnitude of the frequency domain displacement current density, which is also a function to the medium's conductivity, permittivity, and the wave frequency. So you can find the magnitude of tan theta L by taking the ratio of sigma and, and omega times epsilon E. So now we write the Maxwell's equations for lossy dielectric. It does with considering source-free and homogeneous medium. Also, we use the effective permittivity on the second expression. Now, if we want to find the wave equation in terms of E field, we can take curl on the first Maxwell's equation, that is curl of Es is equal to negative j omega mu curl of Hs. Now expand the left hand side of the expression with a vector identity. Then we will get gradient of divergence of Es minus del square Es is equal to j omega mu curl of Hs. Now we replace divergence of Es at curl of Hs from the other Maxwell's equation. As you see, divergence of Es is equal to 0 and curl of Hs is equal to j omega epsilon E Es. Now we simplify this expression. We get del square Es is equal to j square omega square mu epsilon E Es. Now j square is minus 1. We change the side and we will get del square Es plus omega square mu epsilon Es equal to 0. Now we use a constant for omega square mu epsilon E term, and this is called propagation constant gamma. So we say gamma square is equal to negative omega square mu epsilon E, where gamma is j omega square root of mu times epsilon E. So gamma is the propagation constant, and as you see, gamma is a complex number, so it might have a real part alpha and an imaginary part beta. The significance of gamma is it has alpha and beta, where the alpha is the real part and beta is the imaginary part. We also show how to visualize the wave in lossy dielectric. So we will be discussing about wave equations, and we have learned the propagation constant. We express the wave equation with respect to E field and H field, and from this wave equation we can find the intrinsic impedance or wave impedance for lossy dielectric, and we also can find the speed of propagation of electromagnetic wave in lossy dielectric, and we will discuss about the visualization of the wave in lossy dielectric. So we might obtain a mathematical expression as well as a graphical representation for the wave in lossy dielectric, and also we'll discuss about the propagation constant that has two parts, attenuation constant and phase constant. Alpha is the attenuation constant and beta is the phase constant. Here you can see the three-dimensional wave equation in terms of E field, that is del square Es minus gamma square Es is equal to 0, and also in terms of magnetic field, that is del square Hs minus gamma square Hs is equal to 0, and where the gamma is called the propagation constant, which is a complex number and has a real part, the attenuation constant alpha, and the imaginary part, that is the phase constant beta. So gamma can be written as alpha plus j beta, and the gamma that we derived before is equal to j omega square root of mu times epsilon e. We will be finding the expression for alpha and beta from this gamma. Here we are considering the wave equation in terms of E field, that is delta square Es minus gamma square Es is equal to 0. So now assume Es is equal to ESZ AX, meaning that ES has a polarization in x-axis and the function of z, that is varies in z direction. So the wave will be propagating in z direction and polarized in x-axis. So then the one-dimensional wave equation becomes d square Exs over dz square minus gamma square Exs is equal to 0. And the solution to this second order homogeneous differential equation is Exs equal to A e to the power minus gamma z plus B e to the power gamma z, where A and B are two arbitrary constants, and you can find these constants by using some boundary conditions. Now we assume the first part of this solution e to the power negative gamma z is uh, assigned for the wave propagating in positive z direction, and the second part b e to the power gamma z is the wave that is propagating in negative z direction. So we are assuming that the wave is traveling in positive z direction. So that means setting b is equal to 0, and also we assume the amplitude of the wave a equal to ex0. So therefore we will get exs is equal to ex0 e to the power negative gamma z, and gamma, as you know, it is equal to alpha plus j beta. So you can write ex0 e to the power negative alpha z times e to the power negative j beta z. In vector form, we can write it ex0 e to the power negative az e to the power negative bz and the direction of ax. The time domain expressions also shown here. The first expression e to the power x0, sorry, ex0 e to the power negative alpha z cosine omega t minus beta z, and the second one in the vector form. See this expression, you will find we have two exponential terms. One is e to the power negative alpha z. This is the term that is exponentially decaying term, and another term is a sinusoid terms, that is the cosine term, omega t minus beta z term. So we have one sinusoid term and one decaying term. So one term is the propagating term or oscillating term, and another term is um, decaying term or attenuating term. So the meaning of this, the electric field magnitude will be attenuated while it is propagating in lossy dielectric. The rate of the attenuation is depend on the value of alpha. If alpha is higher, the wave will be attenuated faster. Once you get the electric field expression, you can find magnetic field expression by using Maxwell's equation, or also you can use the transverse electromagnetic wave formula. SS is equal to AP cross ES over eta, where a rho is the propagation direction of the wave and ES is the electric field and eta is the intrinsic impedance or wave impedance. So we already found ES, the electric field, and we know the electric field propagation direction. So only we need to discuss about the intrinsic impedance. If you recall the formula for wave impedance, the lossless, sorry, for perfect dielectric, the wave impedance was square root of mu over epsilon. But for lossy dielectric, the formula is square root of mu over the complex permittivity or effective permittivity. And the epsilon E, the complex permittivity, is equal to epsilon times 1 minus j tan theta L. So if you look at this, here mu and epsilon are constants, and 1 minus j tan theta L, it is a complex quantity. It has a magnitude and a phase angle. So unlike the intrinsic impedance for perfect dielectric, now we will get a complex impedance, like impedance with a phase angle. So we can write the magnitude of the impedance is eta magnitude and the phase angle is psi eta. Says the magnetic field intensity is equal to the propagation direction is Az times 1 over the impedance is magnitude eta of eta times the phase angle e to the power j psi eta, and E field is Ex0 e to the power minus gamma z Ax. Now we replace gamma is equal to alpha minus plus j beta. So we can write e to the power negative alpha z times e to the power negative j beta z, and the phase angle of the wave impedance is e to the power negative j eta phi. We shift the phase angle from denominator to the top, so it becomes e to the power negative j psi n Ax. Now we can write Az cross Ax is Ay, that is the direction for magnetic field, and the amplitude of this magnetic field e to the power x0 over the magnitude of eta, we write it as y0, that is the amplitude of magnetic field, and the attenuation factor e to the power negative alpha z, and the propagating wave like cosine factor, that is cosine omega t minus beta z minus psi n. So unlike the perfect dielectric, here we have a phase difference between the electric field and magnetic field. So in perfect dielectric, we found the electric field and magnetic field are orthogonal. Electric field oscillating, let's assume the electric field oscillating in x direction, then the magnetic field will oscillate in y direction, and both wave will be propagating in z direction. And for lossy dielectric medium, if electric field is propagating in x direction, is polarized in x-axis, then the magnetic field will be in y-axis, but there will be a phase angle between electric field and magnetic field. So the phase angle is coming from the wave impedance. As the wave impedance is a complex number, so it has a magnitude and an angle. The angle is psi eta. Now we need to find what is the amplitude and the phase angle. So as you know, the wave impedance has a constant term mu over epsilon, and the denominator has 1 minus j tan theta L term. So here 1 minus j tan theta L is a rectangular form, is in rectangular form. So we can write in polar form, that is 1 square plus tan square theta L square root, and the phase angle will be e to the power j tan inverse tan theta L. Now we can cancel out tan and tan inverse, you will get theta L. So if we take the square root on both sides, then square root of 1 minus z tan theta L will be 1 plus tan square theta L to the power 1/4, and the phase angle will be 1/2. So z theta L over 2. So if you take a square root of the polar component, then the magnitude will be a square root, but the phase angle will be 1/2. Now find the amplitude magnitude of eta, that will be square root of mu epsilon and 1 over tan square theta L to the power 1 over 4, and phase angle is theta L over 2, and where theta L will be is called the wave impedance phase angle phi n. So phi eta is theta L over 2. So we got the magnitude of the eta and also the phase angle of eta. If you want to find magnetic field, you have to find the wave impedance magnitude by using this formula and the phase angle by using this formula. The loss angle over 2 is the phase angle for the intrinsic impedance. Now we need to find the expressions for attenuation constant alpha and the phase constant beta. So as you know that gamma propagation constant is equal to alpha plus j beta, and the expression for gamma is j omega square root of mu times epsilon e, and epsilon e is equal to epsilon times 1 minus j tan theta L. Now if you take the conjugate of gamma, that means the imaginary part sign will be altered. So plus j will be negative j and negative j will be positive j. So now the first part, first j was positive, we change it negative j omega mu epsilon, and this j is negative, so we make the conjugate of this, so that becomes positive j. So that is gamma conjugate. Now if you take the gamma square, the square of this gamma will be alpha plus j beta squared, and this part squared, that will be omega squared mu epsilon 1 minus j tan theta L, and j square is negative 1. So we got omega square mu epsilon 1 minus j tan theta L. Now if you take the square of y gamma conjugate, then it will be gamma conjugate square. That means alpha minus j beta squared, and the term of this will be j square omega square mu epsilon 1 minus z tan theta L. And again the j square will be negative 1, so you'll get negative omega square mu epsilon 1 plus z tan theta L. Now if I multiply y with gamma, gamma with conjugate of gamma, that means we are taking alpha plus j beta times alpha minus j beta. So this will be alpha square plus beta square. So and the right hand side will be, we have j omega, j omega. So you can write negative j omega square, j square, and j square is equal to negative 1. So it will be positive omega square mu epsilon, and 1 minus z tan theta L times 1 plus z tan theta L will be 1 plus tan square theta L square root to the power 1 half. And if you add gamma square plus gamma conjugate square, that meaning this one square plus this square will be 2 alpha square minus beta square. And if you add these two components together, you will get negative 2 omega square mu square. So now you will come up with two expressions. One is alpha square plus beta square is this one, and here is alpha square minus beta square is minus omega square mu epsilon. If you sum these two equations, you will get 2 alpha square at right hand side, and if you subtract them, you will get 2 beta square, and then solve for alpha beta. You will get the expression for alpha shown here and the expression for beta shown here. You don't need to memorize or learn how to solve these expressions. You will not be asked to find the value for alpha or beta. If we ask you to solve any problem that require the expression for alpha and beta, we will provide this on the formula sheet. So on this slide, you can find the expression for the wave propagation speed in lossy dielectric. The formula is omega over beta, and the beta expression we found in the previous slide. So we replace this and you can find the propagation speed. You also, now if you simplify this expression, you can get this one. So omega and omega will be cancelled out, and you can move this square root of 2 on the denominator, on the numerator. So you'll get del square square root of 2 divided by mu epsilon e and this term. So this is the propagation speed. So if you want to visualize the wave, electromagnetic wave in lossy dielectric, you can see the mathematical expression here. So it got an amplitude which is attenuated or decayed while it is propagating. So the decaying factor is alpha, e to the power negative alpha in the direction of z, and there is a propagation term. So it not only attenuated but also propagate. And propagation term is cosine omega t minus beta z. If you plot this expression on a graph, you will see on graph you will find the red, the graph will be a field graph in lossy dielectric is shown in the red line. So the red line shows the electric field in lossy dielectric, and it has two parts. One part is this blue line here on the top, or the cyan line on the bottom. This two graphs is the decaying graph. So the magnitude or amplitude of the electric field or the magnetic field, whatever. So it will be gradually decreasing exponentially with this, like this vector, exponentially decaying graph. And another one, this green line shows the propagation term. So this is a cosine function, and that is propagating. So in perfect dielectric or lossless dielectric, we have only this propagation term, the cosine omega t minus beta z term. But in lossy dielectric, so the wave will propagate and also lost. So the value of the wave or magnitude of the wave will be gradually decreasing or diminishing or gradually decreasing. So this is the field distribution for electric field. You can get the similar um, plot for magnetic field also. If we plot the amplitude of electric field and magnetic field together, you will get the wave like this. So here the blue one represents the electric field and the green one represent the magnetic field. So both electric field and magnetic field, actually if we see three-dimensional plot, electric field will be in x-axis and magnetic field will move in y-axis. Both will be traveling in z direction, but there is a phase angle that is coming from the intrinsic impedance or complex wave impedance will be effective here. So there will be phase or delay between electric field and magnetic field. So this is very similar to the lagging or leading you have learned in RL and RC circuit. We have the same concept here because it is a complex number, so there is a real part and imaginary part. Therefore, there will be a phase angle between voltage and current. In this case, between electric field and magnetic field, and this phasor angle is called the power factor angle that you have learned before. But in this course, we call them like loss tangent, which has the same interpretation, same meaning. So here we have numerical problem for lossy dielectric. So this problem was appeared in some test. So here it is said a TEM 100 megahertz. So it's supposed to be non-uniform, not uniform, because now the magnitude is not constant. So it will be non-uniform plane wave. It's propagating in unbounded non-magnetic dielectric. And the expression of E field is given 80 pi e to the power 0.1 y e to the power j pi y ax. So you have to find the phase constant. Phase constant is 2 pi radians per meter. The attenuation constant is 0.1. The propagation constant will be alpha plus j beta, so that is 0.1 plus j 2 pi, and the unit vector is the direction of propagation. If you see here, the wave is propagating in negative y direction because we have plus sign with b and alpha, so that means the wave is propagating in negative y direction. So AP will be negative AY, the wavelength. So you can find the wavelength here. The solution is followed by the next slide. So you can find the solution also there. So there is formula for finding wavelength, 2 pi over beta. So you can use that formula. Then the speed of propagation, you learn this formula, and the polarization of the wave. So to find the polarization here, you see the wave is polarized in uh, ax direction. So you can write plus minus ax or x-axis, because you see the electric field will oscillate both in positive x and negative x direction. So polarization, if someone write ax or someone write plus minus ax or in x-axis, all are right, because electric field not only oscillates in positive x, right? It goes to positive x and also in negative x. So the polarization of the waves will be AX. The time domain electric field intensity, so time domain will be 80 pi e to the power point on y cosine omega t plus 2 pi y ax. Then the time domain conduction current density. So this is in terms of sigma. So you can write J equal to sigma times E, and E is given. So just we need to write in time domain. Now, the second part of this question says neglect the losses in the dielectric medium. So, if you neglect the losses, then the medium will be lossless or perfect dielectric, and the expression is reduced to this. So, e to the power point one y term is 0 because there is no loss. So, it becomes only the propagating wave. Now, you can find the conduction current density. As sigma is 0, so conduction current density will be 0. Then you can find the relative permittivity epsilon r, intrinsic impedance eta, and the frequency domain magnetic field intensity Hs. So it is said do not use Maxwell's equation. So you can use the expression you learned, that is Hs equal to AP cross Es over eta, and then time domain magnetic field vector A's. So next slide shows the solution to this problem. So here you see the solution to the problem. So the alpha is the radians per meter unit, nifers per meter is the unit for alpha attenuation constant, and propagation constant, the unit is 1 over meter, and the propagation direction is negative AY. Lambda equal to 2 pi over beta is 1 meter, and the propagation speed is omega over beta. So omega is 2 pi f and beta is 2 pi, so you can get on 10 to the power 8 meter per second. The wave is polarized in x-axis. So the time domain electric field intensity and the current density, conduction current density in time domain is the answers are given here. This is the unit for amperes per meter square, unit for current density. The solution of problem 1 is continued here. Now we are assuming the system is lossless. So the conduction current density becomes 0, and we got the beta expression as omega mu epsilon E, and here we have epsilon r, the effective permittivity. We need to find it, and we got ER equal to this 9. Then the wave impedance is mu over epsilon E, so ER equal to 9, and this is non-magnetic medium, so we got 40 pi. And Hs, we use the formula here. So from this formula you got this Hs equal to this, and in time domain it becomes this. Here we solve another example. This is the practice exercise from your textbook. So it says a plane wave has epsilon r equal to 8 and mu r equal to 2. The electric field expression is given. We have to find beta, loss tangent, and the intrinsic impedance, wave velocity, and H field. So we solve for loss tangent. To solve for the loss tangent, basically we are taking the expression for alpha, and alpha is given here. You see in this expression, this is negative z 1 over 3. So you have to take 1 over 3. Negative z is the negative sign is the propagation direction, and z is the propagation axis. So the wave is traveling in positive z direction. So you don't need to take the sign for alpha. You only take the number. So not the variable z. Take only the number. Don't take the sign and don't take the variable. Take only the constant. 1 over 3 here. So 1 over 3 this. Then we take 1 over 3, 10. We put 16 and mu r equal to 2. So 8 times 2, 16 over 2. So this is 8. And if you solve it, you will get 1 plus 10 square equal to 81 over 64. So the solution is continued in this right. So 1 plus 10 square is 81 over 64. Then we can find the tan theta equal to this one. So this is the loss tangent tan theta L equal to square root of 17 over 8. Then we solve for beta. We know the expression. We already derived the expression for beta. And we found it this below square root of 17 over 3 radians per meter. Then we solve for the impedance. 120 pi is equal to mu over epsilon, and then we have 2 over 8, and this formula on a 17 over 8 is equal to tan theta L. So I put this one, and you will get this expression here. So if you solve it in polar form, you might get magnitude and phase angle because it is a complex number. You can leave your answer at this point too. And then the speed, propagation speed, omega over beta, we solve for beta and you know the frequency. So you can find the speed of propagation. And then magnetic field. So magnetic field FBE cross N. And the N has magnitude and the phase angle. It is a complex number. So you will come up with this solution. So you need to solve this or you can leave it here. On the test, we will not ask you to solve this kind of complex problems. So you will be given very simple number that can be solved without calculators, like the problems similar to that question number the problem we solved earlier. Before this, you will be given a problem like the problem we solved before.